Welcome to my video on hypothesis tests for differences in means and proportions. It's common to want to compare two groups, and the logic and procedure for testing hypotheses of individual means or individual proportions can also be applied to cases where we want to test differences in two means or two proportions. In this video, we'll review the hypothesis test logic and apply it to cases where we want to look at the differences in two means or differences in two proportions, and then in a follow-up sequel video, I'll do some examples, including an application of a dummy variable to analyze differences in two means. So, hypothesis testing. Hypothesis testing is a procedure where we come up with an initial assumption about a value of a population parameter, whether it be a mean, a proportion, a regression coefficient, and then hypothesis testing gives us a procedure for evaluating the probability that this assumption is false. So, hypothesis testing typically always has the same elements. There's the null hypothesis, which is the default starting possibility, so maybe it's mu equals 0, or beta is greater than 5 in terms of regression. And then there's the alternative hypothesis that we're testing this against. That can be either a two-tailed test, such that we think the value of the parameter is not equal to the hypothesized value in the null hypothesis, or it could be of the form that the alternative hypothesis is the population parameter is greater than the value specified in the null, or less than the value specified in the null hypothesis. All hypothesis tests have a test statistic, which is going to be used to actually conduct our test and evaluate the likelihood that the null hypothesis is false. And there will also be a rejection region, which is going to be a range of values for our test statistic. And if our test statistic is extreme enough to fall into that region, then we will reject the null hypothesis in favor of the alternative. So remember, with this logic, it's the same logic. It can be applied to many situations. It can be applied to means and proportions, regression. It can be applied to a lot of different things. In particular, we always have the logic where if we can identify or construct a test statistic that equals 0 when the null hypothesis is true and has a known sampling distribution that reflects the sampling error of this statistic, then we can use this known sampling distribution to calculate the probability of getting the value of the test statistic that we did under the assumption that the null hypothesis is true. And then, on that basis, if we think that our test statistic value is small, then there's a reasonable probability that we could have achieved this sample or obtained this sample under the assumption that the null hypothesis is true. So in other words, if we have a small test statistic, there's not enough evidence to reject the null hypothesis. But remember, this does not mean that we accept the null hypothesis. This is not a method which yields proving the null hypothesis is true. So we never accept the null hypothesis. We either reject the null hypothesis or we fail to reject the null hypothesis. The absence of evidence is not the evidence of absence. So never accept the null hypothesis. Now, instead of getting a small test statistic, suppose we get a large test statistic. We get a value that looks fairly extreme, either positive or negative in some cases. Well, in that case, we might think there's a low probability that we could have drawn this sample under the assumption that the null hypothesis is true. All right, suppose we assume that mu equals 10 and we get a sample mean of 100. All right, that would cause us to cast doubt on the likelihood that the null hypothesis is true, and so the safe inference is that the null hypothesis is false, right? Rather than the true mean being 10, maybe the true mean was 90, and it'd be much more likely to get a sample mean of 100. So the real question then becomes, right, what's actually a small test statistic and what's actually a large test statistic? Where do we draw the line? We hypothesize that the true mean is 10 and we get a sample mean of 15. Is that close enough to 10 to not be enough to reject the null hypothesis, or does 15 seem far away? Right? So what really defines what's a small test statistic, what's a large test statistic? That's really a key idea within hypothesis testing. And how we're going to define the dividing line between small and large, or how we're going to think about small and large, is the probability of making what's known as a type 1 error. What's the probability that we reject the null hypothesis when it's actually true? And it's typical under hypothesis testing to want to try to keep that error fairly small. So the most standard value would be 5%, only having a 5% chance of rejecting the null hypothesis when it's actually true. So the difference between a small test statistic and a large test statistic is what's the probability of getting a type 1 error. A large test statistic would give a small probability of making a type 1 error, a small probability of rejecting the null hypothesis when it's actually true. And again, typically a large test statistic would be defined as one that gives less than a 5% chance of rejecting the null hypothesis when it's actually true. Okay, so now we've just replaced, well, how do we draw the line between large and small, with a new question, which is how do we find the probability of a type 1 error? Okay, and we can find that on the basis of the sampling distribution. If we know the sample distribution of our test statistic, we can figure out exactly the probability of getting a value as small or as large as the value of the test statistic we found, under the assumption that the null hypothesis is true. And that's going to be critical for indicating whether our test statistic is large enough to cast sufficient doubt on the validity of the null hypothesis such that we will reject it. Now, that's the logic for all kinds of hypothesis tests. If we focus more specifically on hypothesis tests for a single mean, a single proportion, or a regression parameter, then those all have the same format where we're standardizing our point estimate. Right? We're standardizing our test statistic of x bar or p bar or our sample regression coefficient. And we standardize it by taking the point estimate minus the mean, which is the assumed value under our assumption that the null hypothesis is true, and we standardize that by dividing it by the standard error of our point estimate. So for example, the standard error of x bar. And again, if we know the sampling distribution of our point estimate or our test statistic, like x bar or b in the regression context, then the sampling distribution gives us everything we know, everything we need to know. It gives us the point estimate, it gives us the standard error, and in terms of defining the rejection region, gives us the appropriate number of standard errors. So again, the sampling distribution of our sample statistic is essential in tackling hypothesis testing. Now, what about when we want to look at two samples? Right, there's lots of cases where we might want to look across groups. In HR, you might want to try to understand differences between exempt positions and non-exempt positions. From a recruiting perspective, for example, is there a difference in the average time to fill open positions? Right, so we might think of that as a difference in the true population means in the average time to fill open positions between exempt and non-exempt. So mu exempt minus mu non-exempt. Or in terms of proportions, right, maybe we're interested in, is there a difference in the offer acceptance rate across these two different types of jobs? So that would be a difference in two proportions. But we're not going to observe the entire population. We're going to have to make inferences based on a sample. So what is the best estimate of the difference in these two different means? Well, we know in an individual case that the best estimate of the true average time to fill an open position among exempt positions is the sample mean among exempt positions. And similarly, we know that the best estimate for the non-exempt population is a sample mean of non-exempt population. So it follows directly from that the best estimate of the difference of the two population means is simply the difference in the two sample means. And so we can use the difference in the two sample means to make inferences to learn about the difference of two population means. And it's exactly the same logic which tells us that the best estimate of two population proportions is the difference in two sample proportions. So more generally, if we're interested in trying to make inferences about the difference in two population proportions, we can use the difference in two sample proportions, where those sample statistics are drawn from independent random samples from those two populations. And similarly, we can use the difference in two sample proportions from independent random samples drawn independently from those two populations to make inferences about the differences in two population proportions. Again, this is true for making confidence intervals and for hypothesis tests, the two standard forms of statistical inference. I made some other videos applying this to the confidence interval case. In this video, we're of course focusing on hypothesis tests. So we have the same exact process and the same format, in fact, of a test statistic that we can use to analyze and test differences in two means as well as two proportions. And so we can standardize those in exactly the same way that we standardize a single mean or a single proportion. And if we know the sampling distribution of our test statistic, which in the difference of two means case is going to be x bar 1 minus x bar 2, the difference in the two sample means, or if we know the sampling distribution of the relevant statistic in the difference of two population proportion case, which of course is p1 bar minus p2 bar, or the difference in the two sample proportions, right? If we know those sampling distributions, we have everything we need to conduct the hypothesis test. So again, we need the sampling distribution for these two important sample statistics, and let's look at that quickly next. So let's start first with the differences in two means. So this is the sampling distribution for x bar 1 minus x bar 2. All sampling distributions have three things that are important for us to know: a mean, a standard error, and a shape. The mean of the sampling distribution of x bar 1 minus x bar 2 is just the difference in the two true population means. The standard error is shown there in the second box. It's just the square root of the sum of each sample variance divided by its respective sample size. If that doesn't look very intuitive, don't worry about it. The main point here is that it's concrete. We can calculate it from our sample and get the needed values we need to make our inference in terms of a hypothesis test. And in terms of shape, you might remember that the distribution of a single sample mean has a t-distribution as long as the sample size is large, and the definition of large is conventionally that the sample size is at least 30, so you have at least 30 observations in your sample. Well, in terms of the difference between two means, it's very similar. It will have a t-distribution as long as both sample sizes are large, which means that both sample sizes have to be at least 30. Now, t-distributions have a degrees of freedom, and so whenever we use t-distribution, we also have to note what the degrees of freedom is. And so in this case, it's the smaller of n1 minus 1, n2 minus 1. So look at the two sample sizes. Whichever is smaller, subtract 1. That gives us the degrees of freedom that we should use when making inferences about the difference in two means. So if our sample sizes are sufficiently large, then we can proceed and we can standardize our test statistic. We can standardize x bar 1 minus x bar 2 by subtracting its mean and dividing by the standard error. And we will fill in values for the difference in the two population means based on our null hypothesis. The rejection region is going to be based on the format of the alternative hypothesis and using the t-distribution with the appropriate degrees of freedom. Now, this has the same logic as in the case of hypothesis testing for single means, which hopefully you are familiar with, right? But let's do an example. Right? Suppose we wanted to hypothesize that the difference in two population means is 5 against the alternative that they're not equal to 5. So we're not interested in a particular direction of difference. We just want to try to test whether the difference in means equals 5 or is different from 5. And if this is true, then we should ask, what's the likelihood of getting an extreme value of the difference in two sample means solely due to sampling variability? All right, suppose we draw a sample from population 1. We calculate x bar 1, the sample mean in sample 1. We do the same thing in sample 2. And suppose we find that sample mean in the second sample is, say, 3 less than in the first. And so the difference in the two sample means is -3. Is that far enough away from 5 such that we don't think that the null hypothesis is true? Or is there enough sampling variability in these two samples such that it would be relatively easy or likely to get these two samples with a difference of -3 in their means under the null hypothesis that the true population difference is 5? That's really the key question for hypothesis testing. Okay, so how can we formalize this? Well, we're going to go back to the sampling distribution, and if the null hypothesis is true, then the distribution of the differences in the two sample means is centered at 5, right? Because again, we're making the assumption that the null hypothesis is true, and so if the null hypothesis is true, the true difference is 5, and so the center of the sample statistic distribution is 5. That's point number 1 on the left side of the screen. And as long as the sample sizes are sufficiently large, right, as long as both of them have at least 30 observations, then the shape of x bar 1 minus x bar 2 is t. It's not literally a t distribution, but has the shape of a t distribution. Okay, but now if we standardize the difference in the two sample means, we end up with the test statistic on the left side of the screen. Right, and under the null hypothesis, if the null hypothesis is true, that standardized variable is centered now at 0 because we've standardized it. We're subtracting off the true mean or the hypothesized mean of 5. And so what we're really interested in is finding probabilities about this standardized test statistic, which is now centered at 0 and is characterized by a t-distribution with the appropriate degrees of freedom. So now we ask ourselves the question, if the null hypothesis is true, right, so if the true population difference in means is 5, what's the likelihood of getting an extreme value of a difference in two sample means? Again, completely due to sampling variability when the true mean difference is 5. Okay, well, we can use our sampling distribution to find critical values of t, such that if we are sufficiently below a negative value of t or sufficiently above a positive threshold value of t, there's only a small probability of being that far away from the center of the distribution. Right, so we can use a familiar table of critical values for t-distribution, and so if we want to use, for example, an alpha level of 5%, and we have a two-tailed test here, that means we want to think about the case where there's only a 2.5% chance of getting a test statistic in the upper tail, and another 2.5% chance of getting a sample statistic that is in the lower tail, so being that far away from the center of the distribution. Okay, so then we've defined our rejection region in terms of a small probability of getting extreme values of t. And so to actually construct our test, or to conduct our test, we observe the difference in the two sample means, and then we standardize that using the circled box, the circled formula over on the left side of the slide. Right, that gives us our t t-statistic, and we compare the actual value of the t-statistic that we get based on our sample statistics. We compare that to our critical values, and we reject the null hypothesis as being true if we have an extreme value of our test statistic. That is, if t is out in one of the two tails, so it's less than the negative critical value or greater than the positive critical value. Now, why would we be rejecting the null hypothesis in those cases? Well, it's because if we get a t-statistic which is that extreme, again, suppose we're using alpha of 0.05, only a 5% chance of making a type 1 error, right? If we get a t-statistic that's way out in those tails, that means that if the null hypothesis is true, there's less than a 5% chance of getting a difference in two sample means as extreme as the one we got, solely due to sampling variability. And so in that case, the safe bet is that the null hypothesis is false, and there's a different set of true population means, which would make it much more likely to get the samples that we actually drew. So this is critical logic around hypothesis testing. What's the probability of getting the difference in the two sample means that we got under the assumption that the null hypothesis is true, simply due to sampling variability? If there's a high probability of observing the sample, of seeing the samples that we actually drew, right, there's not enough evidence to reject the null hypothesis. But if it's very unlikely, for example, less than a 5% chance of getting those samples due to sampling variability under the assumption that the null hypothesis is true, then either we're special and we got an unlikely sample, but the safer bet is that the null hypothesis is not true, and so we would reject the null hypothesis. It's the same thing, same logic for differences in two proportions. We need the sampling distribution, which has a mean, has a standard error, has a shape. The mean of the P1 bar minus P2 bar sampling distribution is the difference in the two population proportions. The standard error starts to get even messier, perhaps, than other formulas. If it's not intuitive, that's fine. The main takeaway here for the standard error is that it's concrete, and we'll be able to calculate it. Might be different twists in terms of how we calculate it, but it will be able to be calculated, so we'll have something we can use. And then the third feature of all sampling distributions is shape, and the single sample proportion has a normal distribution if sample size is large, which essentially cell sizes in the yes category, the no category, to simplify or to generalize, at least 5. Well, it's the same idea, and the difference of two sample proportions has a normal distribution as long as both samples are large enough, which means the number of, sort of yes and no observations in all 4 cases, yes and no in the first sample, yes and no in the second sample, are all at least 5. And then P bar 1 minus P bar 2 has a normal distribution. And so therefore we can take the difference in the two sample proportions, we can standardize it by subtracting its mean using box 1 and dividing it by standard error, which is box 2, and we know that this has the shape of a standard normal because of the result in box 3. And the logic here again is the same. We would define the rejection region. We can calculate p-values based on the alternative hypothesis, whether it's two-tailed or one-tailed. Now, unfortunately, the standard error calculation can vary based on the actual format of your null hypothesis, whether the difference in the proportions is 0 or some non-zero number, but that's just a calculation detail, right? Don't let these calculation details overwhelm you. Testing hypotheses for the differences in two proportions follows exactly the same logic as testing hypotheses in difference of two means, and in fact the same logic as testing hypotheses about single means, single proportions, as well as regression coefficients. So don't let the calculation details throw you off. Really focus on the logic. So to summarize, we can use the same standardized test statistic approach to test hypotheses about single means, differences in two means from independent random samples, a single proportion, differences in two proportions, and regression coefficients. And except for the math, everything is the same. Whether we're doing single means or any of these other cases, the sampling distribution and the properties of the sampling distribution are critical. How we set up null hypothesis versus alternative hypothesis is the same. We can have one-tailed tests, we can have two-tailed tests. How we think about probability of type 1 error or the significance level, how we find p-values, how we interpret p-values, all of those things are exactly the same. The fact that we never accept the null hypothesis, we either reject the null hypothesis or fail to reject the null hypothesis, these are all the same in all of these cases. So don't think of these as 5 different cases. Think of them as just one logic which just has 5 different applications. The math is different, the degrees of freedom might be different, how we calculate standard errors might be different, right? But the logic is all the same. So if you see the commonality in the logic, it will make this much more manageable.